It's Paul with the third and final script for this week on the inverse function theorem for multivariable calculus. This is closely related to Newton's method, but I think the graphs will give you an interesting insight into the 2x2 case. If you haven't already done so, install the numDeriv package. We'll call the library function so that we'll have access to the Jacobian function. And for my first example, I'm going to use the best known example of non-Cartesian coordinates, namely polar coordinates. The function I'm going to define is appropriately called a parameterization function. What it does is take a pair of parameters, r and theta, which together specify any point in the plane, and convert those parameters into a pair of Cartesian coordinates, x and y. I have to write the function in terms of the two components of the vector v, but you can read this as x, the first component, is r times cosine theta, y, the second component, is r times sine theta. And just to check that this works, I'm going to ask, what are the x and y coordinates of the point where r equals 5 and theta equals 37 degrees? Since r likes its angles in radians, I have to multiply 37 by pi over 180 in order to convert degrees to radians. And it says x is very close to 4, y is very close to 3. Things are working fine. Now in this case, it's possible to do algebra and find a formula for the inverse function, which you probably already know. This function is appropriately called a coordinate function. This is a function that, given values of x and y in the plane, specifies the values of the parameters, the polar coordinates r and theta, that will give us that point. And as you know, r is the square root of x squared plus y squared. Theta is the arctan of y over x. And in r, there's a function named atan2 that does exactly what we want. Given any values of x and y, be they negative or positive, it figures out the angle between the positive y-axis and the direction from the origin that leads to that point. So let's try this out on x equals 4, y equals 3. It says r equals 5, theta is equal to 0.64 radians. If you start with parameters, compute x and y, and then use the coordinate function to get your parameters back, you discover, yes indeed, the composition is the identity function. And as is always the case when you have two functions that are properly inverses of one another, the order doesn't matter. If I first run the coordinate functions on 3 and 4 to get the polar coordinates r and theta, and then run the parameterization function, I'm right back where I started. Now the nifty thing about the inverse function theorem is that it says even in the case where you cannot write formulas for the inverse function, you can still figure out the derivative of the inverse function. And you're already familiar with the single variable version of that says that if you want to evaluate the derivative of an inverse function g at a point y0, which was in the codomain of your original function f, it's just 1 over the derivative of f evaluated at x0. This is the same formula in multivariable calculus. So let's start out with a pair of polar coordinates. R equals 5, and theta is very close to a value that corresponds to 37 degrees, but this time I've made it exactly the angle whose tangent is 3/4. Now let's calculate the derivative of the parameterization function. The parameterization function was param f. Its derivative I'm going to call param j, j for Jacobian. And there it is. It's a perfectly nice 2 by 2 matrix. And what the inverse function theorem says is simply, if you invert that matrix, there's its inverse, you have calculated the derivative of the inverse function without having had to calculate the inverse function itself. So let's check that. In this case, we've actually got a formula for the inverse function, coord f. Let's calculate its Jacobian, and we get exactly the same matrix. Arguably, that's all there is to the inverse function theorem. But now let's try looking at what's going on using a contour plot. This will work very nicely when we have inverse functions for functions from R2 to R2. Let's maximize our real estate, and let's define separate functions for the first polar coordinate r and the second one theta. R is the square root of x squared plus y squared. Let's check that that works. Well, it didn't. I see why. That's why I always try out my functions before using them where I can't see the result. You may be a more disciplined coder than I am and can skip that step, but I'm sloppy. I check up on my work, though. Okay, let's pick a range of values for x and for y to do our plot. We'll look at x between 2 and 6. We'll look at y between 1 and 5. We will use this crazy function expand grid to make this gigantic list of pairs of values. And then we will use the function that makes a matrix out of these function values by applying the function r to all these pairs, and 1 means we're going to apply it to all the rows. Now we're set up for using the contour function, and there are our contour lines. Big surprise, they're circular arcs. On one of those circular arcs labeled with 4.5, the distance from the origin has the value 4.5, and so on. Now we do the same thing for the second polar coordinate function. I'll call that function theta. This one works too. Carry out the same mysterious steps, and this time draw the contour lines in red. I have to remember to use add equals true, so I will overlay them on the first one. And there are the contour lines for the coordinate function theta. They're straight lines heading out from the origin, the angle with the x-axis being the value of theta. So if you look at the contour line that is labeled with a red 0.5, that's the line where y equals 1/2 x. Now let's pick our usual point, 4, 3, and let's consider making a not too big change in x and y, an increment where x goes up by 0.2, y goes up by 0.5. You can see that represented by the green arrow on the screen. We are changing the values of x and y from the values at the tail to the values at the head. Now, because I plotted these contour lines, I can fairly easily read off from this diagram that after I make those changes in x and y, r is very close to 5.5 and theta is very close to 0.7. And this graphical technique is actually fairly satisfactory when you're dealing with functions from R2 to R2, but there's a way of doing it entirely algebraically. Let's compute the derivative of the inverse function. We've already got it. It's called coord j. So I ask, what happens if I take the coordinates evaluated at v0, the values of r and theta that go along with my point 4, 3, and then add on to that the derivative of that function, its Jacobian matrix, matrix multiplied by the increment vector h. And when I do that, I get 5.46 as my value of r. That looks just about perfect according to my diagram, and I get theta equals 0.6995. That's good too because the head of the arrow is just about on the line 0.7. If you want to deal with other coordinate systems in the same way, it will work very nicely. There are examples in the homework, and this might turn into a very interesting term project as well. I want to move on to an example, however, where there's no geometric significance whatever. This is an economic example, which is sample problem 7. In this example, you are spending amounts x and y and coming up with two different effects. Happiness, as represented by the first function, which is x plus the square root of x times y, and the total cost, which is x to the 1.5 power plus the square root of y. So you've got two different features of your benefits package measured by x and y, and you have a function which gives the amount of happiness generated among your employees and the dollar cost of providing those benefits. If I set x equal to 4 and y equal to 9, then this function says the happiness I get is 22, the cost is 11. How exactly one quantifies happiness, I don't know, but that's economics. I'm not going to worry about it. Okay, let's try doing the same sort of plotting. We will plot values of x ranging from 2 to 6. We'll plot values of y ranging from 7 to 11. Use expand grid to create a long list of pairs of values. And then we will apply the happiness function. That's the first component of my function f of v, and I discovered through experimentation I have to make an explicit definition of it in order for apply to work correctly. So there it is, and now I can plot my contour lines. On the horizontal axis is the amount x of the first thing in my benefits package. On the y-axis is the amount of the second thing, and the contour plot shows values that lead to happiness ranging from 13 up to 30. The greater the benefits, the greater the happiness. Now we do the same thing for the cost function. This is the second component of the function that I've named f of v. Now I can apply it, and I overlay the contour lines in red. You say, hey, aren't they supposed to be perpendicular? No, not in general. For coordinate systems, they usually are, because people like to use so-called orthogonal coordinate systems where these contour lines intersect at a right angle. But in a more general context, you don't expect them to be at right angles. You might say, but if they're not at right angles, couldn't they be parallel? Yes, they could be parallel. And that's precisely the case where the Jacobian matrix can't be inverted and the inverse function theorem won't work. Now, in the problem as stated, the challenge is to adjust the benefits package to reduce the cost to 10 and do so in such a way that you reduce the happiness only to 19. And with my contour plot, I can read a pretty good approximate solution off this. If I take 7.9 for y and 3.72 for x, those green lines intersect where the black contour line has the value 19 and the red contour line has the value 10. So this is a way you could solve this pair of equations graphically without using any calculus, multivariable or single variable. Having got this good an approximation, you could improve it further by using Newton's method. But here's an alternative. We say, While we don't have a formula for the inverse function that converts happiness and cost into the components x and y of our benefit package, we can still compute its derivative. How do we do it? We calculate the Jacobian for the original function f that converts x and y into happiness and cost. And then, having evaluated that matrix, we invert it using the solve function. We ask, what are the desired increments in happiness and cost? Answer, since the happiness is going to go down from 22 to 19, the first increment is -3. The cost is going down from 11 to 10. The second increment is -1. Start with 4 and 9. Add on the derivative of the inverse function, matrix multiplied by the increment. And what we get is x equals 3.72, y equals 7.94. That's very, very close to what we read off the contour plot. Now suppose you have more than two variables. If you have more than two variables, it's very difficult to draw meaningful graphs. There are programs that attempt to draw graphs in a plane that you can visualize as representing 3 dimensions, but it's hard to read good values off them. On the other hand, this inverse function approach works perfectly well. All we have to do is calculate and invert a Jacobian matrix. So it will serve you well if you have problems like this involving more than two variables.